So I'm here today with Peter Woodhead, who contacted me because I'd done a presentation which some people watching this video might have seen about two interesting topics: the hollow Earth and the expanding Earth. And Peter had contacted me because he'd also been researching these topics, having become interested. So we're going to spend a good bit of time talking about that, and what Peter has ended up showing me today is, I think it's really extremely interesting, and he's kind of almost joined these two topics together, kind of, as you'll see as we discuss this. And the way that he's done this is very, I think, very sensible, and it explains a number of the anomalies, which some of which we're going to try and go through today. And he's tied together that with some of the scientific research that he's discovered about, for example, the formation of planets. So we're going to talk about that, and we're going to talk about things like the dinosaurs and how that they could have walked the Earth when they, if they walked the Earth today, for example, they'd be too heavy and their joints would not work properly because they'd be too heavy, basically. So we're going to try and cover all of that, and I think hopefully you'll find this is an interesting presentation. So thanks for inviting me, Peter, and for your hospitality today.
Nice of you to come and indulge my little theory.
Well, absolutely. No, it's not. It's a great pleasure, and I think what you're showing me, as I say, is very, very interesting. So perhaps we'll start off then, and sort of, if you can tell us a little bit about background, as much as you want to tell us.
Well, I've been researching several different ideas over the years. Most of them you might consider to be conspiracy theories, but such is life. That's what interests me. I hadn't really looked at the thought of a hollow Earth before about 12 months ago, and basically I'd been watching one of Richard's shows, Rich Planet, where he interviewed a guy called Keith Hunter. And he interested me because he was talking maths, which I'm quite interested in, and he was also talking about the ratio of units of length, which I think he was using a fathom, 6 feet.
Oh yeah.
And the multiples of those fathoms, and the in relation to the circumference of the Earth. And although it was a bit baffling, it was interesting.
Yeah.
And it got me to thinking that, well, has the size of the Earth changed? He was looking back into antiquity, I don't know how far back, and he reckoned that the world then had a 360-day year, a 30-day month, and this figure of a fathom fitted perfectly into the circumference of the Earth, and that he'd noticed that we are out of sync with that now, having 365 days and a larger planet circumference. So it just got me thinking, and so as you do, I've been on the internet looking at different things. Came across the work of James Maxlow and Neal Adams, who've both done fantastic computer-generated images of our Earth going back in time and then forwards again, and the relationship of the what is the continental area now and the new crust formed in the mid-sea ridges by volcanic action.
And I think that's one of the things where that's where you have to start looking at why the Earth is changing, because when they did, I think the key factor that Maxlow highlighted, and I think probably Neal Adams as well, is that when they did these oceanic surveys, there was no ocean floor which was older than 180 million years, I think, was the figure.
Yeah.
So that was a bit of something they couldn't really explain, that the Earth was meant to be much older than 180 million years. So where had the other ocean floor gone? And so they came up with this idea of subduction, didn't they? That the older ocean floor was being subducted or under the continental shelf.
I think it was, I don't know if it was in the early 50s, a guy called Alfred Wegener, and he came up with this theory of continental drift, which is what we were. And so the theory of continental drift required, with a fixed size Earth, it required somewhere for this new ocean crust to be disappearing, and so they came up with this theory of subduction, which is the new, or rather the new-ish, if you like, seabed comes up against the continents and then is drawn underneath the continents. So then you get to have a fixed-sized Earth. But what Adams and Maxlow says, it's not a fixed-sized Earth. There's no subduction, and the Earth is getting bigger, and this new crust that's been formed in the centre of the oceans is pushing apart and creating an expanding. I call it expanding. Neal Adams gets quite upset at the term expanding.
We're talking about that,
he insists that it's growing and that new mass is being created somehow. That's where I sort of lost the plot a little bit.
Because I think we need to pause on that, because this was one of the, if you go and look at the expanding Earth as look at the evidence that James Maxlow has put together, it's pretty compelling that he's actually right, that the Earth is indeed expanding. And once you look at, because he's gone through all the geological records and looked at the way that species have migrated and flora and fauna have migrated, and he's gone into a lot of detail, hasn't he?
He has, and he deserves the credit for that.
He does indeed, and I've looked at that and I've written to him. I think we've both written to him and exchanged emails with him. But as the key point is, when you talk about the expanding Earth, which we're going to go into more in a few minutes, is if it's expanding, how is it expanding? And then there are two possibilities: either we've got a constant mass there that's kind of inflating or whatever, or just expanding if you want, and the mass is not actually changing, or even Maxlow's talked about this, and Neal Adams talked about this. So they think the mass is actually increasing. And the primary reason why they think it's increasing is because of the gravity effects, isn't it? Which again we're going to talk about, which if I've understood that right, isn't it? They've based the idea of the increase in mass, connecting that to the increase in gravity, haven't they?
Yeah.
But then, of course, all the normal mainstream scientific community will say that's just nonsense, because mass just isn't created like that. How can this mass be created? And I think what you've done, Peter, from what you've shown me today, you've come up with a very good sort of explanation for the increase in gravity, but the mass staying the same.
So I found the images they'd created fabulous, basically, and compelling. You can hardly watch either of their videos and not think, well, that's got to be right.
Yeah.
But where it all falls down is when they get to the point of, well, where's all this mass come from? And I see the logic, and I thought along the same lines for a considerable length of time. But the increasing mass of the Earth, and as Neal Adams would say, the increasing mass of the Moon, are not compatible with maintaining a realistic orbit of the Moon and the Earth. Because if over the last 300 million years our mass has increased by a factor of 5, and probably a similar figure for the Moon, then using the simple equation of inverse square law of gravity, you'd have these two objects that are getting bigger and bigger and attracting each other more and more, and it wouldn't have taken 300 million years for us to crash into each other. So from that reasoning, you have to dispel the increase in mass, which is good because there's no realistic theory of where this mass comes from. They both stated that it's some kind of transfiguration of energy into mass, which they can't explain it. So I've dispelled with that in my theory. There's no need for any more mass. The increase in mass does explain the increase in gravity, but as we'll see later, I've got an explanation for why gravity was a quarter of today's value in the time of the dinosaurs.
Yeah. Okay then, Peter. So so one of the mysteries that is not really, we see it as a mystery, but it's not really seen as a mystery so much by other people, is, for example, the size of the dinosaurs. These were huge land-based creatures, and these days the only creatures of that size, like the blue whale, for example, live in the oceans, where they have buoyancy, so they can have a larger overall body size. But again, if you do the maths, and I mean, we've talked about Stephen Hurl's book, haven't we? Dinosaurs and the Expanding Earth, and we both stumbled upon that, I think, under similar circumstances of looking at this expanding Earth research. And he points out in there, and he does some, because I think Stephen Hurl's an engineer by background, and I've got a software engineering background, as some people might know, and you're in the building trade, so you're used to dealing with heavy weights, aren't you, and so on. What Hurl calculated was, he did some surface area and volume ratio calculations, and he said that, like, their knee joints could not possibly have worked with the strength of bone and the type of material that the bones are made of, which I think is fairly well known. They would not have been able to support their own weight. So we are then led to conclude, and also, for example, the size of various flora and fauna, which are much larger than, not just the dinosaurs. We've had insects, I think, that were 2 metres long and stuff, haven't we? They've got, I've talked about this in the Expanding Earth presentation that I did. So we've got those problems in nature to look at and to solve, and so some people have concluded, like us, that gravity was actually weaker then. The force of gravity was lower.
Yeah.
And so we then, as we said a few minutes ago, stuck with, well, if you've got a lower force of gravity, it means one way of getting that is to have less mass. But as we're going to see, it's not necessarily going to be like that, is it? So if you want to sort of add anything to that.
Yeah, I did struggle with this for a while. In fact, using the standard formula for the attraction of gravity between two objects, i.e. a dinosaur and the planet, if you go back to the reduced sized Earth when the dinosaurs inhabited it, if you take the centre of the Earth as being the centre of gravity, then you actually get a greater figure for the force of gravity in the time of the dinosaurs. However, it's a tricky one, because the simplified formula for the attraction due to gravity assumes it works great on a planetary scale, because the distances between them are huge. Whereas when you're actually stood on the surface of the attracting body, where actually is the attraction coming from? Yeah. And in the models that I've done, in the time of the dinosaurs, you can actually place the points of attraction to maybe 1,000 kilometres deep or 600 kilometres deep.
Right.
Yeah. But today, with the expanded planet, the point of attraction is actually 300 or 500 kilometres below our feet. So then, because it's an inverse square law, the figure under the equation was 4 times greater back then than it is now. Therefore, a quarter of the gravity.
Yeah.
Between the dinosaurs and the Earth, even though we're on a bigger Earth. The mass I'm contending is the same, but it's the point of attraction beneath our feet that makes the difference.
Yeah,
and it's easily shown by mass. It took me a while to get my head around it.
We're talking about the mantle being a shell, aren't we? So of some kind, and then the key concept here again that you've shown me today is that. Maxlow and Neal Adams and others of their ilk assume a solid all the way to the core, pretty much.
It does account for the gravity, because you get a bigger mass of Earth and you get more gravity.
Yeah.
And I think where Maxlow missed the point was he was using that simplified equation.
Yeah.
where you take the centre of the planet as being the centre of gravity.
Yeah.
And it just as I said, it gives you a figure in the era of the dinosaurs of 3 times greater than now, not a quarter of.
Yeah, yeah.
And so he dismissed that very early on, whereas what he needed to do was perhaps expand his search for the real centre of attraction, which is not the centre of the planet.
Right, and then you were telling me that quite a lot of this has come together in your mind, fairly recently. I think you started looking at this about a year ago, was it, or something? Or?
Yeah, but really only got round to polishing off the maths in the last few weeks. It's easy just to take even Maxlow and Adams's compelling videos. It's easy to just assume that's where we're up to. And what I think I've done is take it a step further and said that's not the extent of what we can deduce.
Yeah.
We can deduce things to make it all work, because they were left sort of with having done all the hard work. I'm not claiming to have done anything that they haven't done. It's just they hit a wall, and now we're on the other side of that wall, and we can explain.
And what you showed to me earlier, I think, is one of the key starting points, and that's this article about the way that planets are formed. Although the article that you showed me is not specifically about planetary formation, it really is. Because I don't think you mentioned that, but it alludes to planetary formation because they've observed this disk of material around this other star, haven't they?
These astronomers are looking at an accretion zone of a newly formed sun, and what they're saying is that the birthplace, if you like, of what will become planets in that star's system. So what they're saying is, I'll read this to you.
Yeah.
That they've imaged a snow line in the accretion disk surrounding the sun-like star TW Hydrae, a young star 170 light years from Earth. They state that starting from the star and moving outwards, water is the first to freeze, forming the first snow line. Further out from the star, as the temperature drops, more exotic molecules can freeze and turn to snow, such as carbon dioxide, methane and carbon monoxide. So they're suggesting that the area of the ice, water being frozen to ice, is in the area of an orbit of what might eventually be forming an Earth-like planet. So that turned on my head everything I thought I knew about formation of our planet, because as you learn in school, you think back to and the textbooks, they showed some kind of boiling hell on earth scenario where everything's hitting each other and high temperatures. And what I realised was, well, out in space it's pretty cold, minus 273 absolute zero. So this ice and some of these such as methane, they're not freezing at zero, they're freezing at minus 100 and something. So I'm thinking, well, there's no ambient temperature to create all this heat that we have in the textbooks. So I thought, well, what would our Earth be like if it was newly formed? And if it was mostly, well, a high percentage water, and all the other stuff that we've got on our planet was in the mix, if you like, what would it be like? And I think for a long time it's going to be very cold. Now, as I think we're going to be going on to soon, NASA did an experiment on the space station.
This is great, yeah, when you showed me this. I've
Yeah,
never seen this before.
It's a bit light-hearted. I don't know what made them think of it.
Yeah.
But as you'll see, I think you're going to put it on. You play the video, and they showed a revolving golf ball-sized lump of water, sphere of water, because it's weight. Yeah,
it's done on the International Space Station, isn't it? So
then they inject that first with some air bubbles, and as it's spinning, the bubbles all migrate to the centre. Then they inject some tea leaves,
yeah.
and the tea leaves migrate to the outside. And I thought, well, that's turning on everything on its head that I've been taught,
yes.
because we're supposed to have not a molten, but an iron core to our planet.
That's right.
And I thought, well, if this is what happens in space, then the heavy stuff goes to the outside and the light stuff goes to the inside.
Here we have a rotating sphere of water about 25 millimeters in diameter, and inside this sphere are a whole bunch of little tiny air bubbles. And we will see what the angular acceleration due to rotation does to these air bubbles as a function of time. What you are observing are the bubbles moving to the center axis of rotation. As a function of time, they will form this rather tightly packed bubble core. These bubbles are kept from coalescing from a small amount of added surfactant to the water. Here we have a rotating sphere filled with bubbles and tea leaves, and as expected, the bubbles go to the center and the tea leaves go to the outside edge, along with a few chunks of orange peel. Here we have a rotating sphere with bubbles and chunks from breaking up a small vitamin tablet. And the bubbles go to the center core, but the vitamin chunks seem to stay in their location dispersed through the sphere. And from this we deduced that the vitamin chunks have a density near that of water.
And it just made me pull the ideas together that in this TW hydrate, when it starts to form its Earth-like planet, the solids are going to go to the outside and form a crust, and the inside, which is frozen methane and mostly water in the form of a sort of a slush, for want of a better word.
We're trying to come up with a good word.
Yeah, anybody who's got a better word for slush. Yeah. So we find ourselves with this pre-Earth, if you like, which is predominantly slush. Over the course of billions of years, the heavier elements are going to reach the outside of the sphere. So those elements are going to form the crust and also the mantle. And then lighter liquid elements, such as the water and ice, are going to migrate inwards. So for us ever to warm up, because as you go down through the crust, it is warmer. So there has to be a mechanism for the warming of our planet, and that basically is done by the breakdown of uranium and thorium in the mantle, which creates heat. That heat in turn is going to warm up our icy core. And over the period of time, that ice and frozen elements of other gases are going to thaw. So then we get to the point where we've got a liquid core, but it's still being heated. So as it continues to be heated, it's going to come to the boil. And when water comes to the boil, you get steam. Steam, in turn, can exert enormous amounts of pressure. And as more and more steam is created by the heating of the inner core, the pressure becomes that much that it forces cracks in the surface of that crust. Those cracks then will vent magma, and they'll also vent steam. So you get the situation where the Earth is splitting along its continental margins and being vented, but not vented enough to stay a constant size. The pressure is such that the continents are then prized apart along the weakest link between them, and then you get what we now see as mid-oceanic growth of the new crust, which is formed from basalt and volcanic activity. And as Maxwell and Adams have shown,
Maxlow and Adams, yeah.
they show the continents being pushed apart by this new crust which is being formed along lines, as everybody knows, between Africa and South America. You can see that those two continents did fit together.
Yeah, at one time, yeah.
And what the graphics that they've done, which are fantastic, they've shown this from every angle of the planet. Yeah. They show quite clearly that there's no subduction and that this new seabed is young and it's less than 200 million years old. And so there's the direct evidence from the sonar work done by the US, I believe, in the 60s, and we are now at the point where we can explain the mechanism of why these continents are being pushed apart, and I call it steam-powered Earth expansion. Evidence of this phenomena can be seen all over the solar system, on planets, our moon, other moons, and I think the time has come for this to be established as fact. So we have the mechanism now for Earth's expansion, and we also have the explanation of why for the first 4 billion years of Earth's history there was no expansion. There was no expansion because the inner core of our planet was just frozen stiff, and until it transformed from ice to water and then to steam, there was no mechanism for it to expand. But expand it has, and it's expanded exponentially. The heat is generated as just turning a vast reservoir of water into steam, and that steam is irresistible in its expansion.
And then, of course, the other point which I was impressed with when I thought about what you'd put on the table here is, because one of the big mysteries in all of this, one of the big Earth mysteries, is where the oceans came from, isn't it?
Yeah.
So essentially we've essentially got the answer to that, haven't we?
Yeah. I've done some maths on this, and I've calculated that probably all the oceans, the water in all the oceans, is little more than 1 or 2% of what was once subterranean, if you like.
Yeah.
And that the oceans that we have now, that water has been forced through these cracks in the mid-ocean ridges, and that's the source of the water, or the vast majority of the water on our planet. I believe that there was water, surface water, but there were only shallow seas, as most people who are familiar with this subject will say. There were shallow seas, and that's where all these fossils are found, in the remnants of these shallow seas that might be miles up in the Alps or wherever they find these fossils. But there were once shallow seas, and that's where a lot of the early development of life went on, up until and including the dinosaurs.
Yeah. And so, I mean, we've got a couple of answers to some of the fundamental questions in the Earth's formation, and because a lot of people have said that the oceans probably came from comets crashing into the Earth over millions of years, and that doesn't really fly too well, really, does it? Because of the amount of comets that you'd need to fill up the oceans would be probably fairly substantial, and and I don't think that's certainly not regarded as the absolute answer to the mystery of the formation of the oceans, is it?
I've never considered that.
No, neither have I. But I think on that subject, when we're discussing this, and whether, for example, there might be things that might trigger this outflow of water. Well, I think if we've, taking what you said, one thing that I suggested to you, I mean, we've only just discussed this in passing, really. We haven't really gone into great lengths to analyse it all. But is this idea perhaps that if we've got this expanding, boiling kind of chamber inside the Earth, where the steam is coming out, what would happen if we had a large asteroid or cometary impact, coming in and affecting the mantle? Yeah,
I mean, we can't prove it, but it could stimulate by if it hit in a vulnerable area, it could stimulate a great outflow of both magma and water from the inner core. So you could have had a sudden deluge, in theory, and that could have been, the flood. Many cultures talk of a flood completely engulfing the planet.
Yeah.
Well, if you look at Maxlow's and Adams' description of the formation of mountains, it's to do with the changing shape or radius of the Earth. So if you can imagine back on the pre-Earth, there wouldn't have been mountains. The continents would have been probably undulating with a few shallow seas, but not have the great height of the mountains. So the volume of water that we have on the surface now could easily have covered all the continents with several kilometres of water.
Yeah, yeah. So again, we've got observations here, and to explain, what's been happening with the volume of the oceans and how they've changed. So I think that's an important thing to consider, because we're not, one of the things that you pointed out, one of the fundamental things is that we're not changing the mass from the time of the original formation of the Earth. I mean, not substantially anyway. You might have bits and pieces that accrete and so on, but that'd be a very, very tiny sort of fraction of percent of the overall mass. Whereas these other, both Neal Adams and James Maxlow, have talked about an increase in mass.
Yeah.
And so that's again one of the fundamental things which
this is different.
It's different, and this explains it, I think, very well. And I think one of the other things that you've looked at, Peter, was the sort of surface area of the pre-expansion Earth, and you tried to do some calculations on that. If you'd like to describe, how you went through that process.
Yeah. Well, being unable to do the CGIs that Maxwell and Adams had done, I decided to go on the internet and find out what the surface areas of the continents are now, the area of the continental shelf, which is also part of the pre-Earth shell, if you like, and ignore everything to do with the oceanic crust. So by doing that, you get a fixed area, which is the continents now plus the continental shelves. And by doing the maths, you can come to a figure for the size of the pre-expansion Earth. Then as it's expanded, it's been added to by the oceanic crust.
Yeah.
So I got a figure of something like 59% of the radius of today's Earth, which fits in pretty well with Maxwell and other researchers. And
so you basically went from the surface area, you said that would be obviously a spherical surface area, and then you could go using the 4/3 pi r cubed or whatever, or pi r squared. You can then go back and work out what the radius was by using that calculation. Yeah.
So then what I did was I calculated the not the mass but the volume now of the Earth.
Yeah.
Because we're saying. I'm saying that we've got the same mass and the same volume, if you like, as we had 300 million years ago.
Yeah.
So doing the mass for today's radius of the Earth and subtracting the volume of the pre-expansion Earth, you get a figure of what is not there, if you like.
Yeah.
And pretty much that gives you a radius of what is now the gaseous part of the internal makeup of our Earth, and that has a radius of 5,900 kilometres.
Right.
So if you take that away from the actual radius of the Earth, you get a figure of 400 and something kilometres. So that is the thickness of the shell of the planet. So that's made up of the crust, the mantle, this watery element, and then the rest is gas to the centre of the Earth.
So you actually managed to quantify the extent to quantify the sizes of these components within sort of certain limits.
Yeah. You can only work out the volume because we don't know what the actual ratio of solids to liquids are.
No.
It's just that area. I've done 3 different calculations, which will no doubt go in.
Yeah.
But there's nothing to say that any of those are right. It could be greater solids or greater water content. But the fact that there is sufficient water subterranean to produce enough gas, steam, over time, that the Earth's expansion will be exponential, as has been shown by other people.
Yeah.
And I believe that will continue until there's some kind of equilibrium reached. But I believe by that time, who knows what the planet will look like.
We don't know, but indeed, you came to the sort of same conclusion as Maxlow, didn't you? Because you were talking about the Earth ending up as something similar to some extent to a gas giant.
Yeah.
So
and there again, it does throw water on his theory and Adams of a growing Earth, because an exponential growing Earth, it's going to gobble up all the matter in the solar system in no time at all.
Yes.
And if all the other planets are expanding, then where's it coming from?
Yes. Yeah.
So, sorry to say, Adams and Maxlow, but you've got it wrong.
The other thing that we'd spoken about was this Youngman Practice, who's a South African who'd modelled the seismic signals that had been sort of sent down through the Earth during earthquakes, and they come out the other side. And various scientists have claimed that this proves certain things about the structure of the Earth, and Youngman Practice has also spoken about that. So if you just tell us your thoughts on that.
Yeah. Basically, one of the first things that Youngman Practice says is that these seismic waves don't flow through liquid. And the first thing I would say to that is we've got a crust, and under that crust we've got a fluid mantle. So my take on that is that these seismic waves are not flowing through that mantle because they would be absorbed because of its liquid state, even at temperatures and whatever. So I think all the seismic data is just recording waves that are being refracted in between the upper and lower edge of our crust.
Right. And
that I believe it's up to the seismologists to prove anything other than that, because Youngman Practice, he said, he found evidence that there was a hollow core to our planet.
Yeah.
So I think the ball's now in their court to dismiss what we're saying, rather than us try and prove them wrong.
So that gets us on to, I think, the topic, as I was just saying there, of essentially we're not talking about hollow Earth, before people misunderstand that.
No, what I'm suggesting is that this superheated reservoir of water, which deep below the mantle, is being and other liquids are being turned to gas. So this inner volume it's not a vacuum.
No.
It's full of high pressure, high temperature steam for the most part, and other gases, because as we've said before, I believe all the gases, or most of the gases, migrated to the centre, and that's where most of the gas is going to be.
Right. And so that then takes us on to the general sort of idea of mass distribution, isn't it? Because one of the things we didn't talk about properly before was when we were talking about the gravity changing. That's one of the big mysteries that I think you've also solved.
Yeah.
In the way, because essentially what I summarised it in that it's the mass distribution which causes a change in gravity, not a change in mass. It's just the distribution of the mass, isn't it? So if you want to tell us a bit about that.
Yeah, initially when I did the accepted formula for the attraction due to gravity, and I thought it would just come like that, and that you know, it would be easy, but it didn't, because when I first did the calculation, as I think that Maxlow has, if you take the centre of gravity of that pre-expansion Earth, be it 3,000 and odd kilometres, and then compare it with the attraction due to gravity today, you actually get a figure that is 3 times greater then than it is now. So the dinosaurs required it to be a quarter of what it is now, and that threw me for a bit.
Yeah.
But eventually I realised that, as you said, the distribution of that mass on the pre-expansion Earth, the centre of that, the centre of gravity, if you like. You probably do better with the maths of explaining exactly where it might have been, but I estimated it to be 600 to 1,000 kilometres deep. Yeah. So then so taking that as being the r in the r squared bit of the calculation, you end up with a figure of between, well, let's just take the higher figure of 1 million. Yeah.
Right.
So you're dividing the sum of the two masses and the gravity constant. You're dividing it by 1 million.
Yeah.
When you come to our Earth as it is now, most of the mass is concentrated in less than 500 kilometres. So the centre of that might only be 400, 500 at most. So when you square that, you get a figure of 250,000. So that is a quarter of the distance that we had in the pre-expansion Earth,
right,
which exactly equates to the dinosaurs living on a world that had a quarter of the gravity that we have now.
Yeah, yeah.
And that just sort of gave me the pat on the back, if you like, saying, yeah, you are right in what you're thinking.
Yeah, well, I mean, that again, you know, backs up the constant mass sort of scenario rather than the increasing mass.
Yeah.
You know, because again, like, and then the other thing we didn't talk about, we should have talked about, but that's just reminded me, is the issue of the core, because it's assumed that the Earth has an iron core, doesn't it? And you know, tell us about that.
Right. Yeah. I more or less dismissed that as soon as I saw the NASA thing with the heavier elements going to the outside. But obviously, it's in all the textbooks, so you've got to. The reason why it finds itself in the textbooks is because somebody's assumed that something metal down there is creating a magnetic field, which is keeping life possible on the planet. But as we've discussed, there's a lot of new thinking going on in astronomy, and one of the new threads of thought is the electric universe, and the fact that all the suns and the galaxies and planets are connected electrically. And this is easily shown to be true of the relationship between the Sun and the Earth, that we're electrically connected. So the Earth is spinning. It's in an electric current or an electric field, and I think that's all you need to generate the magnetic field. Is the rotation of the Earth, which is the crust and the mantle have got high proportions of metal of iron, and I don't think you need an iron core. In fact, we haven't got an iron core, and that's that explanation really, as best I can do.
Yeah, I mean I agree with you, because as you say, the only reason why they need an iron core is to explain the Earth's magnetic field. But as you know, as we would now contend, if you've got a kind of partly external reason for the Earth's magnetic field, which is this electrical interaction between the Sun and all the other planets, and indeed, you know, even sort of going beyond that into the you know, sort of nearest star cluster and that sort of thing, you know, you can extend it to that. Then we don't, as I say, we don't need the. I mean, no one's ever seen the iron core. Nobody's ever drilled down that far. It's just assumed to be there purely to explain the magnetic field, and then that's the same with the needed expanding mass for the expanding Earth under Maxlow and Neal Adams. They need the expanding mass to explain the change in gravity, whereas what you've proposed with the calculations you've done is that it's simply the mass distribution which is causing the change in gravity. So again, we're looking at that differently and using the available evidence to explain those phenomena. We just mentioned briefly earlier on that what you've proposed, we've actually already got some other evidence for that's been picked up in the past few sort of 20 years and whatnot, hasn't it? So
even the last few days.
And we're going to come to bring it bang up to date, as you say. So tell us about that.
Yeah, what I'm suggesting is the method for the Earth's expansion can be and is being witnessed on moons and other planets. Neal Adams has done some CGI of Mars and has done some of the Moon, but the most compelling ones that keep coming along recently are of some of the outer planets' moons, which in some cases are pretty much a similar size to the Earth. And what we've been seeing is we've seen the Cassini probe, which has identified venting of either liquid or other gaseous material through a hard surface, and also the Hubble has witnessed it.
So the Hubble one was Europa, wasn't it? Which is the moon of Jupiter. But I think also one of the other probes would pick that up on Europa. I think probably the Galileo probe will have photographed that as well. I'll check on that though.
Right.
But the Hubble, I think obviously maybe they've continued to image it with Hubble to see if the rate has changed or whatever.
But what we're seeing is more than one example of liquids beneath the crust of these moons being forcibly ejected. The Cassini probe seeing venting, and it just backs up what I'm saying, that these moons have got a hard crust that's containing liquid that has been heated up and brought to the pressure such that it forces itself out through wherever the weakest point in that crust of that moon is. And pretty much that is confirmation of what I've been saying. They're having their own bits of steam or gas-powered expansion, and it's either going to vent or it's going to expand. And I think you're going to get a bit of both on these moons.
Yeah, and I suppose it may, maybe depend on the actual makeup of materials as to how much expansion and how much venting you actually ended up with. And
exactly.
The other...
Exactly. On Enceladus, I don't know if that's the right pronunciation. Yeah. The liquid is predominantly methane, and the solid is frozen water, ice. Yeah. And you've got the ice taking the part of what would be our crust, and then the methane taking the part of what would be our water.
You're further out in the solar system.
You're further out, it's colder, and it's not warm enough for the water to become liquid.
Yeah, yeah. And the other famous example, which which is probably exhibiting venting, is on Io, Jupiter's moon, where they had that was the first time a volcano was photographed in the solar system. That was also undergoing sort of tidal gravitational forces, or so they tell us. Yeah. So maybe that is also, that is an example of the venting from this very similar process.
Yeah, maybe they've got the same kind of radioactive decay going on, or maybe it's an electrical phenomenon of being part of the electric universe, or it could be a tidal effect, because some of these moons have tremendous tidal effect because of the orbits that they take around their mother planet. But either way, heat's being generated, the liquid under that crust, or the crust of these various moons, is being heated up and then ejected. And
you can't argue with that, can they? Because that's
because that's what they're telling us.
Yeah, but they're just saying that it's causing venting, whereas in a different scenario over a longer period of time, I think we can see it's causing expansion. Okay, well I think we've sort of covered all the main points, and I know Peter's got a lot of other topics that he's looked into. We've discussed that in passing, and Peter's got some interesting and rather difficult experiences that perhaps we might discuss another time. But overall, I think I'd like to thank Peter for spending time with me going through all of this, and hopefully somebody's going to look at this and it's going to be a bit of a eureka moment for them.
Yeah.
Because I think I've certainly had that effect having seen this, and I'm quite impressed the way you've put this together in a very short space of time. And I think it ties together a number of phenomena that we've both been looking at. So I think that's congratulations, basically. So
thank you very much.
Okay. All right. So again, thank you, Peter, and we may come back and do another part and discuss some more things in the future. We'll see how it goes.